So thanks so much for inviting me to come and join you all this evening. We're going to have a very brief tour on where we are in our understanding of cosmology. But before we want to do that, it is the eve of International Women's Day, and so my compliments to the organisers for having a brilliant set of diverse speakers. This talk, as it is International Women's Day tomorrow, is dedicated to all of the ladies of lensing. We're going to be talking about gravitational lensing today, and these are all of the fantastic female astrophysicists who have made the work that I'm going to show you today possible. So without further ado, where are we with cosmology today? Well, our best understanding of the universe comes from this absolutely iconic image from the cosmic microwave background. This is the radiation that was emitted right after the Big Bang. I hope it's a picture you've seen before. Stephen Hawking's called an earlier version of it the face of God. I like to think of it as a bit like a battle plan from the early universe. So the red spots you can see here, these are hot spots in the universe where gravity is pulling structures together, and that's heating up the radiation. But the blue spots is where the opposite's happening. So it's kind of strange to think about radiation photons being able to push matter around, but that's exactly what's happening. It's got so hot and dense that eventually the photons have enough pressure to push the matter apart again and cool. And that's what you can see here in this battle plan. And you can do a statistical analysis of this pattern. This is the power spectrum of this pattern. And it's basically the number of hot spots and cold spots on different scales. And that tells you some really fundamental facts about our universe. I should point out here that the red line that you can see here, this is not just a spline fit to the data. This is a theoretical model of what you'd expect this pattern to look like if you had a universe made up of 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. Now, if we were in a conference of cosmologists at this point, we could probably split the audience into two parts. We're going to call our first group of cosmologists the smug cosmologists, and I hope that translates across the pond. They are rightly so. They are rightly smug because they have created this amazing data set. This represents huge advances in our understanding of space technology, statistics, big data analysis. It's absolutely huge. This is a team of hundreds, possibly thousands, who have put this together and have told us these fundamental things about our universe. Now, our other camp of cosmologists, of which I'm a member, we're going to call the embarrassed cosmologists, because if you talk to anyone who's not a physicist, they're like, oh, that's great, well done. So what is this dark matter? And you say, kind of hope that the particle physicists would have found one by now. Going to give them another 10 years, pretty confident they'll have either created one at CERN or caught one in their underground layers. Good. And then they're like, okay, fine, I'll give you 10 years on that. What's this dark energy stuff? And you're like, really no idea. Really no idea what that dark energy is, but it appears to be causing the expansion of the universe to accelerate. So our job now is to actually try and answer these people, to actually try and explain what is this dark energy. And the simplest explanation comes from Einstein's field equations, which if you've done GR recently, you'll be happy with. And if you're not, you're going to be a bit worried at this point that the talk has taken a bit of a bad turn. Don't worry, don't need to know what these terms are. Terms on the left-hand side deal with the curvature of space-time. Terms on the right deal with mass and energy, and basically these equations say that mass tells space and time how to curve, which is going to become important for the lensing technique that we're about to use, or curved space-time tells mass and light how to move. Now, if you remember your GR undergraduate course, you'll remember that this term here comes about in your derivation because you can do a constant of integration. So that's fine. This is called Einstein's cosmological constant, and this term can mimic, can give you an accelerated expansion of our universe, which is crazy. This additional energy term can come from Einstein's cosmological constant. So if you're happy with maths telling you how the universe is, then we're done. But a lot of us aren't so happy with that, because every other term in Einstein's field equations has some physical meaning. You know, we can relate it to things that we understand. And this cosmological constant at the moment is just there because mathematically we can put it in there when we do the derivation. Now, your simplest explanation of Einstein's cosmological constant is that it is coming from a vacuum energy. So you can look in quantum physics and it will tell you that if you have an expanding vacuum, you will create additional energy from the virtual quantum particles. Lovely, great, done. Apart from the fact that if you take the energy that this mechanism, this quantum mechanism would predict, the first stars and galaxies that Anna was just telling you about would never have formed, and we wouldn't be here to be chatting today. So that's that one out the window, and we're left with two sort of brands of models. Either there's a new weird energy force field in the universe, so we used to 4 fundamental forces, maybe there's a 5th, or maybe Einstein's theory of gravity isn't complete. So maybe there's some mechanism where gravity behaves differently on different scales. And so our job is now to invent different probes of the universe to test out these different models. If you're wanting to test things with gravity, or then you're best off having a probe, an observational probe that is sensitive to the curvature of space-time from gravity. And that's exactly what we're doing. So this is a technique called weak gravitational lensing. It is just photonics. So you look at millions and millions and millions of distant galaxies. Their light travels roughly 7 billion years across the universe. It depends how deep your data is. Each time that light goes past a dense region where space and time has curved, its light path gets bent and distorted. So the images that you actually observe of these very distant galaxies, they tend to line up with each other. And so your job is to go and look for these alignments between the galaxies to infer where all of the invisible dark matter is in our universe. And if you do this at different epochs, if you look at galaxies at different distances away from you, you can see how the universe is evolving with time. And that gives you a handle on what the mysterious dark energy is doing. So you can confront both theories about dark matter and dark energy with this method. Great, we all say, apart from the fact that this cartoon is absolutely nothing like what we see, the type of distortions that we're looking for. The shapes of the galaxies change by about 1%. Your telescope will introduce distortions at the level of 10%. Add on the atmosphere as well. It's like looking for a needle in a haystack. But amazingly, after 20 years of working on this as giant international teams, we can actually do this. We can measure these very subtle distortions in our images and use that to infer where the dark matter is and how it's evolving with time. So let me give you an example here. So I hope that Zoom is communicating this image to you in enough resolution that you can see there are lots of tiny blue dots. Now, those are background galaxies. Their light's taken roughly 7 billion years to reach us. Now, in the foreground, you've got these big yellow galaxies. Those galaxies have taken about a couple of billion years for their light to reach us. Now, if our theories about the universe are right, those yellow galaxies that you see there should be housed in a big cloud, a big halo of dark matter. And that should be curving the whole of space-time. So the images of those background galaxies are going to be distorted. Their light is going to be bent as it goes past this dense clump of matter. And we can use that signature to detect where the dark matter is and how much of it there is. Now, as I said at the start, we don't know what dark matter is, but I'm quite sure if it had a colour, it would be pink. So this is where the dark matter is in this region of sky. And we can do this process across the whole sky. So this is an absolutely tiny patch of the sky, but we can use some of the largest telescopes on Earth to make huge surveys to map this out. Now, there are 3 surveys competing at the moment to do this. So I co-lead the what I like to call the scrappy European underdog. We've got a smaller telescope and we've got a smaller survey, but I think we're still doing quite well with the kids survey. Now, my fine colleagues at Duke are part of the co-leading, actually, the big major players in the dark energy survey, which is the big American project. You know, in America, your cars are bigger and your cans of Coke are bigger. Your telescopes are bigger as well. No, it's absolutely fantastic survey. And there's also the Japanese survey, which wipes the floor with both of us. It's an 8-meter telescope, and it's going to be absolutely awesome. They're just running slightly behind us, but their data is absolutely exquisite. I could show you the mass maps from all of them, but there's no point because the dark energy survey one is by far the biggest and the most beautiful. Here it is. This is their map of dark matter across the sky. This map you can see here in pink. Luckily, the dark energy survey agreed with me that dark matter is pink. What you can see here is you can see that there are clumps over densities of dark matter and a kind of a web-like structure, which is exactly what you'd predict from our theories about dark matter and dark energy. And this patch of sky that they've mapped out here spans about 1/8 of the whole sky. It's absolutely phenomenal, exquisite data. Now, what do we do with it? Oh, and I should show you this as well. If you can see dark matter in full resolution, this is a numerical simulation of what we think it should look like. So the direct observations of this invisible stuff in our universe is looking very similar to the numerical simulations. But we don't do things with just looking at maps and things like that. We actually do things with statistics. So this is the statistic that we use. We're looking at how aligned are galaxies as a function of their separation. So when galaxies are close to each other on the sky, their light, as it travels through the universe towards you at your telescope, is going to go past the same large-scale structures. And so it's going to experience the same curvature of space and time. So it's going to get bent and distorted in the same way. And so galaxies that are close to each other on the sky, you find that they're quite aligned, strongly aligned with each other. But as galaxies move apart from each other on the sky, their light goes through different parts of the universe, different large-scale structures, and so their alignment is weaker. And this makes us sensitive to different parameters about our universe. They've got 2 cosmological parameters here. One tells us how much dark matter there is in the universe, and the other one tells us how clustered the dark matter is. And we can do this at different epochs in the universe. So the reason why we started all this, the motivation was so we didn't have to be embarrassed telling people we didn't understand what dark energy was. Well, dark energy is going to change the way that clustering of dark matter happens over time. Imagine it like another battle. You've got gravity of the dark matter trying to pull everything together, but dark energy is causing the expansion of the universe to accelerate, which makes it harder for those dark matter structures to form. So what dark energy does is it slows down how quickly the dark matter can cluster over time. So you end up with horrendous plots like this, where you split your data up into all sorts of different bins of galaxies at different distances away from you, and you're looking for the correlations between them and trying to dissect the information about how the dark matter is evolving and changing with time. And this allows you to set constraints on these cosmological parameters. Now, we'll take a little trip down memory lane here. Yes, I do have enough time. We first made these sort of measurements on a big scale almost a decade ago now, before that iconic map that I showed you at the start was released. And we set constraints on these 2 parameters. So there's a plot here. The y-axis is how clustered the dark matter is, and the x-axis is how much dark matter there is. And you kind of get that banana-like shape. We can't really distinguish between the 2. But those are the sort of the region of parameter space that we're happy with. Now, the grey ball you can see there is the constraints that you get from that cosmic microwave background data that I showed you at the start. So even though that data is taken right after the Big Bang, it can still predict how the dark matter should cluster today and how much of it there is today. And you can see that they don't quite agree with each other. What you really want is for things to lie on top of each other. So different independent experiments make the same predictions or make the same inferences about how our universe looks today. So this meant that we got told a lot that we were doing something very, very wrong, which, yeah. So then we got a bigger telescope and we carried on, but we were very worried about wanting to get the right answer, which isn't really very scientific. So I want you to take a little meta pause here in my talk now, and I'm going to ask you all to think about the project that you're working on right now. How do you decide when to finish? How do you decide when to publish? And for the PhD students online, it's probably when your PhD supervisor tells you you're ready to publish. For the PhD supervisors, you probably decide they're ready to publish when they get the same result that you got before, maybe. It's very hard to know when to stop, when to publish, but there is this kind of unconscious, or in some cases conscious decisions that you keep working until you get the result that you want, and then you stop because you're absolutely exhausted. So we learned our lessons from the fantastic particle physics community. We took on board their methods to blind the data, so you're insulated from that final result until you've passed all of the null tests that you can possibly think about. And I'm really delighted this has been adopted by the whole community now, because it's really important when you're answering big questions like, have we maybe got Einstein's theory of gravity wrong? You want to be absolutely sure that your data is telling you the final result, not just the result that you've got to because you're tired and you want to stop. Okay,
Catherine,
so
just to let you know, you've got 4 minutes left.
Thanks very much, Chris. So these are the most recent results from the kilodegree survey and the dark energy survey, and should highlight Marika Asghari and Alexandra Amon here, who co-led these two projects. But this is a teams of many, and should also particularly highlight Troxel in Duke as well, who also co-led the DES analysis. So guide you around the plots again. It's the same one that I just showed you, just to remind you the y-axis is how clustered the dark matter is, the x-axis is how much dark matter there is, and you want to compare that banana with the constraints from the cosmic microwave background. And both of these experiments are finding that it's on the low side. Independent measurements from very different teams. So one of the fun things that we're doing at the moment is we're actually working together, these two academic cousins who have been competing with each other for many years have now joined together to analyse these data sets together. I think with Andrea was saying at the start, you know, it's really important that you have independent teams working on things to sort of hive mind and really improve your analysis. Right, we're not the only people finding strange things, and this is the next talk which Dan Skolnick is going to tell you about. Similar scenario, comparing constraints on a fundamental parameter of our universe that's been predicted by that iconic map from the cosmic microwave background with direct measurements today. But what Dan's going to tell you about is measurements of how fast the universe is expanding today, the Hubble constant. And again, a disagreement between direct measurements of how the universe appears today and what you'd predict from the data from right after the Big Bang. What does it mean? Okay, so this data from the Big Bang, it doesn't directly tell us what our universe looks like today. To do that, you need a model. You need a model to evolve the universe from the Big Bang to the present day. And what we're finding is that our universe is too smooth and it's expanding too fast, which goes in the same sense. So the faster the universe is expanding, the less opportunity there is for dark matter to clump things together. So these two independent measurements of our universe today and the disagreement with the early universe is in the same sense. But unlike Dan's results, which is 5 sigma and therefore particle physics gold, ours is still at the 2-3 sigma level. So we're not quite there yet, but it's really interesting times because either something's not quite right with our analyses, something's not quite right with the Planck analysis, something's not quite right with both, or something's not quite right with the model. And the question is there something wrong with our dark energy model? All of this analysis has been done assuming Einstein's cosmological constant is the origin of the dark energy model, even if we don't understand where it comes from. Is there something wrong with our approximation that dark matter is cold? Maybe there's something wrong with our approximation of dark matter all over. So these are the questions that we are now starting to answer. And when there's a controversy in science, your best way to solve it is to get more data. That's where we're going. So lots of new data on the horizon. The dark energy spectroscopic instrument is taking data. This is going to produce a 3-dimensional galaxy survey. I haven't had time to talk to you about that today, but that's a whole other new direction that we're taking in cosmology. The Vera Rubin Observatory, where Chris is right now, this is very exciting. I am uber excited about this project, not only because it is named after the Trailblazer who made us all believe in dark matter in the first place, but because it's going to be totally epic. It's going to survey the entire night sky on repeat for 10 years, giving us the widest, deepest image of our universe. There is nothing not to love about this instrument. I'm so excited to be part of it. We're also going into space. So the distortions that we're measuring in the images of these galaxies are absolutely tiny. They're 1%. So when the atmosphere blurs your galaxies like this, it makes your life really hard. So when you go into space, everything is much higher resolution and your life is a lot easier. So we have the launch of Euclid and Roman coming up. Duke, again, a big leader in Roman. And these two telescopes are going to give us that crystal clear vision of the universe. And now we were all set for Euclid to be launched early next year. Sadly, and quite rightly, ESA has pulled the launch of Euclid from the Soyuz, Russian Soyuz launch that was going to be launching it. So there's now a bit of uncertainty about when Euclid will be launched with an Ariane launcher instead, but that's the right decision for Euclid and ESA to have made. But it will launch, and it's going to be the combination of Euclid and Vera Rubin and Roman all together that's going to really help us overcome our embarrassed cosmologists, so we can really tell people what these dark components in our universe are. For any undergrads and PhD students in the audience who are just starting, there's a book you can read. It's free to download. Gives you a really basic introduction to all of the stuff that I've talked about today. And thanks very much for inviting me, Chris and everyone in Duke.